Good morning, everyone. I'm Carsten Eickhoff. I teach computer science and its applications in biomedicine at Brown University. And I'm very excited to be here today. I hope to talk a bit about one of our recent papers. Let's try and keep this, even though there's a small crowd here, but don't be shy. Let's try and keep this interactive. We have question time afterwards, but really if anything throughout is unclear, too fast, too weird, just give me a shout out and I'm happy to discuss these things as we go. So the title of this paper is quite a mouthful. So it's Diagnosis, Prevalence versus Efficacy in machine learning-based diagnostic decision support. It's going to be a tiny bit different from some of the tech meets medicine papers that you may have seen. So a lot of these papers follow this pattern of here's a problem, here's a solution, let's measure how well the solution works. This paper here really focuses on carving out a problem and measuring the extent of that problem, right? And what we're going to look at is different types of diseases, how frequent they are, and what this frequency does to the effectiveness of our machine learning-based models. All right, so, and this is all going to be in the context of trying to diagnose people. So we'll look at electronic healthcare records that come in different modalities, and then we want to ideally assign the correct diagnosis to a person. So what should this person be treated for? Okay, so that's a bit of the context of this work, and this appeared at AMIA, which is the American Medical Informatics Association earlier this year. So this was in March. All right. Before we dive into really the technical details, I guess, of this paper, I want to quickly say a few words about the context in which this all happened and who we are as a lab and what we do. So I guess, general premise here is that a lot of the work that my students and I do follows this theme of computer science and often data-driven methods, right? So machine learning and friends meet biomedicine. It's not always clinical, but often there's a clinical application to it, right? And really the three big areas that we work in is, I guess, the traditional machine learning, data science, which I understand as information retrieval, NLP, right? So all of these applications, and then the biomedical sector. And some of these things are more biology leaning, others are more on the clinical medical side. And then in particular, if we zoom in a bit on the clinical side, what we see is that there are three big questions or three big points on which machine learning or technology in general can help. First one is diagnosis, right? So looking at a person and all the different views that we may have, right? That might be imaging, it might be time series, it might be different tests, it might be wearable devices, it might be your social media stream even. And what that says about the person's likelihood of having a certain disease, right? Now, once we have a hypothesis of, oh, it could be this disease or maybe that other one, the next class of problems we are interested in is testing. So what's the right test in order to distinguish between different diseases? And then finally, therapeutics. Now that I have a strong suspicion of what this person really has, what's the best course of action? And you'll probably have come across this term of precision medicine, right? And that very much lives at this point here, where we are really interested in, out of maybe 5 different possible therapies for a certain disease, which one is most promising for this particular patient. Okay. So who does all the work? So my lab at the moment has 7 PhD students. It's the folks that you can see on the slide here. But then we have also 3 postdocs and something in the order of 30-ish undergrads that work in teams towards these different projects and problems. And just to give you a bit of a flavor for what this is, besides the concrete thing that we're talking about today, I just wanted to very briefly discuss a few recent projects that we have worked And then also sort of on the sidebar, what kinds of modalities are we looking into here? So what's the application, but also what types of data are we working with? So one recent project looked into CT scans of the brain. They come in slices. So you have this stack of slices and you want to find out where in this stack, in the little blood vessels in the brain, where is there an obstruction, right? So whereas typically those are blood clots and that can lead to stroke and similar complications. And we are interested in, first of all, determining, is there such a blood clot? And then second of all, where is it located, right? And that helps you in surgical planning. And the data that we're using here is really radiology imaging data, right? So this is a traditional computer vision type problem. Another clinical application that we recently looked into was for people that had invasive surgery, right? So open heart surgery, for example, trying to predict who will experience complications after surgery and who will be fine, right? So this is a setting where often we see complications as people had their surgery and now they are on intensive care. And especially at night, the ratio of doctors to people on intensive care can be somewhat low. And we want to ideally have a system that monitors all these vital signs that come in over time. And we want to have some form of indication that says, well, these people seem to be doing fine, but you, dear human doctor, put your attention on these 3 people because they seem to be the cases that are a bit in the middle ground where there may be some risk. Right? So, and most of the data that goes into this is time series. So is continuous values that develop over time. So blood pressures, heart rates, things like that. We work a bit on drug design, right? So if you think about the traditional setting in which we come up with new drugs, that would basically be us synthesizing a certain molecule, a certain substance, and testing clinically first on animal models and then eventually on the human clinical tests, what medication, first of all, does something useful for humans, and second of all, doesn't kill us, right? Because a lot of substances that would have beneficial uses are also toxic. Right? So there's always this trade-off. So obviously, there are a whole lot of theoretically possible substances, chemical molecules out there that we could synthesize and then do the mouse model test and then do the human test, right? So this doesn't scale. So what we try to do here is use machine learning in order to predict which of these billions of candidate molecules are actually promising, right? So which molecular structures look similar to existing drugs or do something that looks promising for a certain disease. We looked a bit into genome sequencing data and trying to forecast from a bunch of mutations that we've seen, and those typically are involved in cancer, so this is mostly oncology, and try to forecast what other mutations is the research community maybe not even aware of, but they look likely based on the data that we've seen, right? So this is very interesting. So this whole topic is called hypothesis generation, and it's the idea here is that we, instead of just waiting for things to happen, we try to anticipate research directions and also medical problems before they even become a big issue. Right? So part of that might have been 2 years ago spotting COVID and saying, well, that looks rather worrying. We should look into this already. And then really, as we turn to textual data, one could try and automatically answer biomedical questions, right? So you could say, I'm going to go read 1 million biomedical papers. So me, the little robot, right, the system. And now what we want to do is we want to be able to answer questions. So if someone goes in and says, can my dog get COVID? You want this machine to be able to say, well, yes, and here's 3 papers that evidence that. And then, and this is the topic that we're going to look into today on the diagnostic side. So how can we automatically diagnose people based on data that we may have about them? And in particular, do this in the context of infrequent, rare diseases, right? And we'll talk in a moment about why this is difficult. And what we are using here is both textual data as well as time series. And this is sort of an interesting class of problems where you look at multimodal input data. So where it's not just time series, not just text, not just imaging, but you really try to draw from all of these sources in order to produce a strong. Before we go into the details of that, this is sort of a very, very quick schematic of how I think about the world of medical and general machine learning really problems. And this scale here goes from the left, from structured data, all the way to unstructured, right? So we start here with something that's maybe time series, and we know we will measure every minute. So in well-defined intervals, we'll measure maybe a heart rate, right? So I know column 3 is always heart rate, and it progresses over time. This is very easy, very well behaved. That's something that we like as machine learners, right? And then we have maybe somewhat less structured data, such as genome sequencer reads, even less structured data such as imaging, right? So radiology, where you know it's always going to be an X-ray, it's always going to be a chest, but you might not know what each individual pixel is, right? Because people have anatomical differences, and you might not know, oh, pixel range so till so is always going to be this particular rib, right? So you have to, you can assume the rules of physics, right? So there's first of all, the rib is going to be continuous, it doesn't just suddenly end and then start again. And it's always the same context on content here. So we know it's just CTs. It's not any. There will not ever be a photo of a cat in there. And then all the way at the business end here of where stuff gets really messy and exciting, we have text, right? And text is really tricky because there are many different ways of writing down the same factual statement in different surface forms and different words. And really to express yourselves in different ways, right? So, and this is really here going all the way away from the nice world of the physical reality and the laws of physics, all the way to this human artifact of language and how to interpret that. And especially this end of the world is what I'm very interested in and where a lot of my work happens. Okay, so that as a bit of context. So if you think about this scale, all of these projects live somewhere on this scale. And if you look at what we're talking about today, it's going to be drawing from this end and this end, right? So sometimes there is data and some textual data. Okay, good. So at this point, let's jump in and think a bit about diagnostics. So I want to spend one quick slide on why is diagnosis hard. Why might that be hard for people? So doctors tend to struggle with 2 or 3 different things about diagnosis. So the first one is the disease that you actually have is rare, right? So this is something that you, as the doctor, have either never seen or you've read about it in med school, and it's maybe 20 years ago. So it's something that's not at the forefront of your mind. Right, so there's all kinds of cognitive biases going on that will make you think about the common case, right? So if you go see your doctor in flu season, you will have the flu very likely, even though you broke your hip. So, and that's of course putting it maybe a bit strongly, but these effects are at play. So stuff that is very rare, that we see very rarely, we don't consider likely. Either we're not aware of it, or we think, oh yeah, it could be this thing, but it's really so rare that it's most likely something else. And then 2 other reasons that we are maybe not so strongly focusing on today are strange presentation, right? So you have some disease, but your case of this looks different than the textbook, right? So you just have an odd case of the whatever it is. And then finally, comorbidities are tricky, right? So you have 2 diseases and together they look like nothing of the 2, right? So that also is a big problem. So today we are focusing on rare diseases, so stuff that's infrequent, and we have basically this continuum here where we go from common diseases to, this is the threshold for rare, right? So the definition is 1 in 1,500 people in the population has this, and then it can go all the way to maybe 1 in a million people, these ultra rare diseases here. So one could now argue, okay, but if it's rare, why would I care, right? Because hardly anyone has this. So and just to briefly comment on that, so each of these diseases might be rare, but there are many of them, right? So there are 7,000 to 8,000, depending on where exactly you draw this threshold, rare diseases. And if you count all of them together, the estimate is that around about 10% of the developed world population, so this exact number of 10% was now a US estimate, but it holds very much for Europe and other places, have at least 1 rare disease, right? So this is why this is important. Okay. So let's quickly look at the data that we used. We worked with a data set that's called MIMIC, and that holds almost 60,000 admissions to the intensive care unit. This was data that was collected in Boston over a bunch of years. And it's interesting because it has a very three-dimensional, a very rich view on the patient, right? So we have a lot of interesting data on them. So we have vital signs, right? So this is your blood pressure over time. We have lab results. So if we order a blood count or blood cultures, this is what we'll see here. We know what medication they were prescribed with. And then we have textual notes as well. And this is the interesting part. So here the textual notes are interesting because very rich. Right. And then finally here we have these ICD codes. And they represent diagnoses. So ICD is this big tree-structured taxonomy in which any possible disease or accident, so any medical entity really of interest has a code and may stand in a hierarchical relationship with others. So I might know that that stomach cancer is a form of cancer, right? So I can deduce that from this graph. And if you want to, so I'm not going to go into this right now, but if you want to in your free time, if you perform a web search for funny ICD codes, you'll see that some of them are really comically specific, right? So there's one for being attacked by a parrot, and there's one for being attacked again by a parrot after already having been attacked by a parrot before. And similarly, very, very specific codes in there. So we're not going to inspect these comical ones really, but we really care about diseases, so not so much injuries. And what we try to do is use all of this stuff here, so all this patient information, and try to predict this diagnosis code here that the doctors attached to this admission in this particular data set. Okay. So the task. We are extracting 51 features, and we selected those by hand, right? So we went through and coded up which 50 features or 51 features to include. They come in a bunch of categories. So the first one is demographics. So we know age, sex, marital status. We even looked at insurance status and things like that of the person. We have lab results. So this is white blood cell count, lactate, and so on. We have our vital signs. Right? So this could be your heart rate over time, your blood pressure over time, things like that. And then the final thing, and I don't have that on here, the final thing are these comorbidities, right? So we also know for each person what other things does this person, either what did they have in the past, right? So this person is a cancer survivor and now they have a really bad case of pneumonia. Right. And because there's such an interplay with these different diagnoses, it's interesting to also know, in a way, all the other stuff that the person already has, right? Because some of that may make you more prone to catching some other diseases. And then on the target end, we care about predicting the correct diagnosis in terms of these ICD codes, right? And we're looking at 3 types of models, and here I'm somewhat dependent on your feedback. So please don't be shy. If any of these models you haven't seen in your course, let me know and I'll spend a few words on them. So the 3 families of models that we are looking into are multi-layered perceptrons, so very simple neural networks, support vector machines. I know that you've played around with those, and random forests. Good, so these three types of models, those types of features predicting ICD codes, so that's the menu. Here's the twist. So far, this was pretty standard, right? So this is pretty much your run-of-the-mill machine learning project, right? So you have things, entities of the real world, in our case, patients, described by features. We have some target that we want to infer via classification, and we have some form of formal model that takes these as input, these as output, and learns how to connect one to the other, right? So very, very standard. Now, if you recall the title of this thing, we were interested in frequency of diseases relating to quality of our predictions, right? And that's what we're going to do here. So the twist is that we now take this data set of these 58,000 admissions, and we split that up into by target disease and by frequency of that target disease. So what we're doing is we have 5 subsets here. So the first subset is the 1,000 most frequent ICD codes. Right? So we take all admissions that have as their target diagnosis one of the 1,000 most frequent things. And we see that that keeps 50,000, almost 51,000 of our cases. In a second data set, we keep only the 500 most frequent diseases. So each of these is a bit more frequent than the guys in here, right? So this loses us some 4,000 patients that had something rarer. And then we do this time and again, right? So we keep the 200, the 100, or the top 50 most frequent diseases, and then all the admissions that correspond to these different diseases. Right? And the assumption, and each data set here, so each of these guys here is internally split into 80% for model training, right? So to fit all your parameters, and then 20% test data that we never look at during training that we use to evaluate how well we do. And the assumption here is that as we go down this way, so we have more classes and for each class fewer training examples, probably this is going to get harder, right? So that will be our assumption that we probably for this data set here, we should do worse than we do here. Okay, so that's the setup here. Before we go into model performance, let's quickly look at, as we do this, how these different types of features, right? So remember we have demographics and vitals, lab results, and comorbidities, how they contribute to our model, right? So this is it's really this idea of how predictive are these different types of features. So, and this gives us something like this. So we see that in making these predictions, the lab events were the most predictive ones. So if I take the lab tests away, the model will suffer most, right? So my performance will reduce most. And then sort of in order, comorbidities, so the other diseases that people have are the next most important one. The chart events, so those are your vital signs, are the next, and then demographics are sort of the least impactful one. So the way to read these guys here is basically what's the performance of a model that does not have this type of information, right? So you can see that the performance without lab events is worst, and demographics really don't matter all that much. So this is pretty close to the model that has all of these together. And F1 scores, you probably know what those are. I'm looking to you, organizers. Yeah, okay, so you talked about this harmonic mixture of precision and recall, right? Okay, so let's dive into the results. So this is where it's getting interesting. So again, we're looking at F1 scores, and we're looking at these different data sets here. And the grand result here was somewhat unsurprising, right? So if we look at diseases in the top 50 data set here, and these 3 dots are of 3 different models, then we see that for the top 50 diseases, this is actually something where we get pretty good. But then as we go to the top 100, top 200, 500, or even 1,000, you see that the performance drops very quickly, right? So you have this power law distribution that you see in the frequency of diseases that we now also see in the performance here. So the task gets a lot harder as we have more classes and in each class fewer training examples. Right? And then especially here, as we go to 1,000 or even more, we may reach this point where some of these things we've never seen in model training, right? So both the physician that said, well, I've never heard of this thing, or I've heard about this thing 25 years ago in med school, that person might not get it right at the first attempt. And then similarly, our model has never seen a particular class maybe during model training, and yeah, obviously you don't have a chance of doing well on these. Okay, so this is sort of the thing that we wanted to show here. So very much follows intuition, and this paper really is the first step in this direction of, first of all, showing is there a performance loss as you consider more diseases and as they get rarer? Yes, unsurprisingly there is. But then second of all is we can now also measure how much performance loss there is. And that leads us to the conclusion of today, which is sort of the motivating piece for a lot of the research that we're doing currently. So machine learning is pretty competent at recognizing the heavy hitter diseases, right? So this is your congestive heart failure, this is your diabetes, right? So all this stuff where we have tens of or even hundreds of thousands of training examples. So this is great. As machine learners, we like these problems, right? So if we look into handwritten digit recognition, right? So your MNIST data set, or if we look into dogs versus cats, few classes and tens of thousands of examples in each class, right? So that's how, what we like. This here is a nightmare setting, right? Where the world consists of thousands of diseases and most of them you never see, right? So that's where every machine learner runs away and doesn't want to play anymore. The somewhat, and interestingly, this here, so looking at only the few most frequent diseases, this is what virtually anyone in machine learning in health does, right? So the vast majority of startups looks at 10, 20, 30 diseases and says we are 95% accurate at distinguishing whether you have any of these. That's good, that's nice, it's a good step. But at the same time, doctors are really, really good at this as well. Right? So our vision of why do we do all of this? Well, we do this so that we can hopefully avoid medical errors, so that we hopefully can avoid misdiagnoses, and help these doctors that are under a lot of time pressure, right? But it seems to be that doing only this head of the distribution, where we have a lot of cases to learn from, is already where doctors are pretty good. So actually what they would like to help with is the strange cases, right? So everything that's in the tail of the distribution. But that turns out to be where machine learning also struggles. So what are ways out of this mess, right? And we have a bunch of techniques that we work with at the moment that are promising for helping to repair this. So how to deal with the long tail. There's a class of machine learning models, I don't know whether you guys talked about this in your course, that are called zero-shot learning. Right, so there was a few-shot learning, one-shot learning, and in the extreme cases, zero-shot learning. What this means is you train a system on pictures of dogs, cats, and rats maybe, and you ask it to predict in an image whether it's a dog, a cat, a rat, or a parrot, right? So, and the carrot is parrot is your zero-shot class. So I never gave you a training example, and still I want you to be able to recognize this. So very hard problem. But there's some interesting work going on right now where people try to solve this. And the other one is maybe not thinking about classification so much, but about retrieval, right? So ranking problems where we say, maybe what I want is not a class conditional probability at the very end, right? So your traditional posterior probability of observing a certain patient under the model of diabetes or the model of lung cancer, but instead to say, how similar is this patient to this particular disease, right? So to turn this whole thing from a classification problem into a ranking problem. So in both of these methods are somewhat related and show some great promise for this. And then as the closing thought before I turn this around to you guys to ask questions, I want to end on this somewhat recent finding that misdiagnoses are the third most frequent cause of death in the developed world, right? So in the US, it's cardiovascular disease, cancer, and then misdiagnosis as the third one. So truly chipping away on this here, right? So to say, can we avoid these intermediate steps of where you thought for a year you had a certain disease and you're being treated for this thing, but you actually don't really have this, right? And this is what can avoid a lot of unnecessary suffering or even mortality. So, and that's what we are trying to do, is to use technology to cut down this huge block of misdiagnoses that have very negative outcomes potentially. All right, with that, I'd like to thank you for your attention, and I'm very happy to take questions if there are any.
Thank you so much, Dr. Eickhoff. That was wonderful. If you guys have any questions, just enter them in chat. And then while you guys do that, I have one question for you. So we've seen recently that stuff with your parents can be heritable to you through epigenetic mechanisms. Has parental or familial information been a high impact feature in any research that you've done recently?
That's a good question. Let me quickly think whether we, so we look at, so I guess epigenetics is exciting. I guess there's two things that are often conflated here. So one is really lifestyle, as in your parents have a certain lifestyle, and it might not be transmitted on the genetic, but on the experiential level, right? So because your parents are into healthy eating, you're pretty forced to also eat healthily because you're not the one that does the groceries. And then similarly, I guess a lot of sort of nurture level, if I set the example of regular workouts are a good and healthy thing, that may propagate into you because that's the example I'm setting, right? And then the sort of the counter argument is, no, actually, because I work out regularly on the epigenetics level, I'm actually transmitting that, and you're just naturally forced to do that more. So it's what I'm trying to say here is tricky to pull these apart unless you really do genome, phenome kind of studies. I personally haven't done anything with this. There are a bunch of studies that try to look into this, but there is always this big question mark. How would I get this confounder of all the lifestyle out of this? And that I think to me puts a bit of a question mark on these studies, not so much on whether this would be useful. I think it would be fantastically useful. But it's often, so I guess for us and as researchers, we often struggle with, oh, there's this really great idea, but how would I design an experiment that actually tests for this without all the noise of the real world, watering down my findings potentially.
Okay, cool. That was really amazing. I had another question too. So you talked about using a multi-layer perceptron and support vector machines and random forests for your diagnostic methods. So I was curious on how the actual pipeline is structured, because if you're saying you're going from text data, I would presume you would use something like an LSTM for capturing the associations between words, but is that association captured by human readers who actually pre-screen the data and then send it to the model in predefined parameters, or are you just giving them the documents that the doctors wrote up themselves?
Mm-hmm. So very good question. So in this particular paper here, we did the second version, right? So we defined, so we looked at the health records, we defined features, and then we basically had pretty simplistic rules that said, oh, this thing mentions metastases, right? Or it mentions adherence to a certain drug, things like that. So it's basically taking free unstructured data, so text data, and making it structured by extracting certain binary or ordinal variables. In a bunch of other projects that I'm working on, we do the more grown-up version, and that's what you described. So I think nowadays you wouldn't probably use LSTMs anymore, but transformers. So you've probably seen BERT and Friends, right? So all of these transformer-based, massively multi-head attention models. But that is very much what people do, right? So I think the grown-up version, and I'm doing this, so I'm working with a bunch of technology startups, and with one of them, we try to do diagnostics from text, right? So, and there, one part of the pipeline is very much that. So you take your health record, you represent that in a numeric fashion, right? And that tends to be some version of BERT at this time. And that gives you a dense feature vector, and that you use for inference. But very good question. So it's the usual trade-off is somewhere between those two.
Yeah, got it. Thank you.
Yeah. Anything else that I can tell anyone, whether in Providence or?
Sure, I have one more.
Yeah.
So we often talk about how just trimming your data and picking your features is sometimes the hardest part of the battle when doing machine learning. I'm sure you guys had more than 51 features when you first started with this data. How did you guys trim your features, and how did you get to 51 of your best features?
Right. So there's So I think this is a pretty traditional approach in that we indeed manually selected this. So I think I'll get to the asterisk in a moment of what you would do, I guess, probably in the modern world, right? But what we did here was we looked at all of these potential features, looked a bit at variance of the features, so low variance features you just want to get rid of because they don't mean anything, are not very expressive. And then the trickier stage here, so we didn't do any PCA or anything like that. So all the features that we had in the end are organic things because we wanted this interpretability in the organic feature space, right? So here, when we looked at feature contribution, we wanted our clinical collaborators to be able to say, oh yeah, this makes sense because this is this thing, right? Rather than saying, oh, this is the 17th principal component of the data space, right? The tricky bit with this is, and this requires domain expertise more than it does machine learning expertise often, is to not have any hidden confounders in here, right? So one class that you may have seen is in the data set, so one class of features and the data set that didn't end up in the model here is medication. And medication is often tricky. First of all, it's very tricky to model how much of the medication is currently in the system, right? Because you have these pretty organic decay processes. How long is that in the system? That's different for different routes of prescription. So if you take something oral via an injection. And the other one is medication is not a property of the patient, right? So medication is a doctor looking at this patient and saying, oh yeah, this clearly needs coagulation factors. Let's give so much of this substance. Now, if the doctor already makes a mistake and doesn't prescribe a certain medication, that feature is not there and it's inaccurate, right? So someone should have given some medication, given this patient, but it's not there. So you would, in a way, train your system to listen to what the doctors already did rather than to listen to what the patient looks like. So we very much try to have only features in here that describe patient state rather than expert reaction on patient state. So that's why medication, and you will see that in many studies of this nature, medications are something that we often try to steer clear of just because it's tricky. So I think that's the traditional world, right? So that's if we look at, I guess, random forest and support vector machines, naive Bayes, and all that good stuff, right? There we would do this. Now, in the more modern, I guess, neural network driven world, you would typically not bother with it, right? Because your features are anyway just raw inputs that then eventually go through many nonlinear transformations until you eventually have the thing that goes into your fully connected inference layer, right? So the modern approach to all of this is measure everything, give me tens of thousands of features, aggressively down project that, right? So either use variational autoencoders or something like that, but aggressively go from literally multiple thousand features down to something that's maybe 100-dimensional dense, right? Encode some of the raw information of all of these, and now this I use for model training, right? So, and I think nowadays, other than for pretty toy examples, nobody would do PCA anymore. Right, just because the model will anyway figure out that a certain thing doesn't contribute, right, and it doesn't really cost us much. So that's why I think here we applied a lot of domain expertise just to get these sort of this information leakage out of the system, and that's still important, right? That's still something that you want to do nowadays. But once that is out of the way, this whole business of uninformative features, usually we tend to ignore by now. But it's interesting. I mean, it's clearly 10 years ago, I would have given a very different answer, right? So it's really in the last 7-8 years, I guess, that this has changed a lot in popular opinion of how we do machine learning.
Mm-hmm. Thank you. Yeah, and I have another couple. So just going back to that LSTM direction, I've worked with a few because I dabbled a bit in stock market prediction and was working with birds. But yeah.
So how rich are you now in consequence?
I actually switched halfway between because I was more passionate about a UAV project. So I only set the model up, trained a bit, but didn't actually deploy it in the market.
Okay.
But yeah, so with word embeddings that you're picking up in LSTM, you can often pick up associations that you wouldn't like occasionally have seen, like let's say between boy and man. That's obvious, but let's say in the clinical context, has working with word embeddings often showed you relationships between diseases you wouldn't otherwise have observed?
Yes, or at least that are useful. So if you even if you do the very traditional, so word to bag or glove or these things, right? You do learn very interesting relationships between diseases that are often. I mean, you first of all you get the standard thing. You get synonyms, right? So cancer and tumor and whatever, which are almost synonyms, right? You'll see that all bunches up in the same area of the space. And then secondly, more interestingly, you see that diseases and their symptoms live close by one another in space, right? So tuberculosis will live with other related diseases, but also with symptoms that indicate that disease. And very interestingly, diseases live close by their therapies. So medication that addresses a certain disease will end up being somewhat similar to that disease. And in one project that we did a few years ago, we also saw that. So there we looked explicitly into medication, and we saw that the active agent, so the chemical substance in the drug, and then the branded drug name end up being synonyms, and that's very interesting, right? So you can basically, from prescription behavior of doctors, learn word embeddings that give you, oh, the substance here is actually aspirin. And that's branded as this in France, and it's branded as this in the States, and it's branded as that in Mexico, right? Which is really interesting. So you sort of get these associations out of there. You've probably seen a lot of these vector arithmetic games, right? So there's this king and queen, right, where you subtract the manliness out of some of these things and try to get to the neutral. That doesn't hold quite as well in expert domains. Right, so technical expert domains such as medical, but also engineering, typically hasn't found good examples that follow this. Right, so there are some people that try and actually enforce this in the training process. So we basically mess with the loss function and try to enforce some of these properties that we have basically a translatable vector between a disease and its therapy. Right. But that's something that typically we have to invest more smarts into the model training in order to get that out.
Yeah, I think that's really interesting for me because one, it's not necessarily the main goal you're going for, but even as an intermediary, you're picking up something. And then I guess the last one that I have is more of a bridge between image classification and natural language classification. So I do know for convolutional networks, there's some predefined models like, let's say, Inception, ResNet 50, EfficientNet, or even the Assemble ResNet that just recently came up that are pretty standard models for training. Are there any established ones in the clinical field? I've heard of SciBERT and ClinicalBERT, but haven't personally worked with them. So I was wondering if you had insight on which ones work better in which cases.
Yeah. For vision, we very interestingly also in the clinical world very much use the general pre-trained models, right? So even just because a lot of what you learn in these models are edge descriptors, right? So they don't really care about the high level stuff, the dog and the cat and the airplane and all that, but really the important stuff that takes a long time to learn is, oh, you're a horizontal edge or you're a vertical edge. So all of this we can very effectively learn from ImageNet, MS Coco, and all these other data sets. So I think a lot of folks, so if you want to do spot the tumor in a lung CT or something like that, right, in a chest CT, you'll probably use something that's some form of DenseNet, ResNet, or UNet, something like these, pre-trained on ImageNet, and then you will sort of fine-tune in your domain. So that's very much the case, and I don't think that there's much that there are many models that are really specifically trained in the medical world, just because we typically suffer from data sparsity, right? So the medical world is just tricky because everything is to some degree protected information, so we can't easily share patient information, and that's why we tend to not have quite as large data sets. Right? So therefore, there we take pre-trained models from the general domain and translate that then into our domain that we care about. For text, it's a bit different. So indeed, there you have BioBERT and SciBERT and all that stuff. I've worked with both of these. BioBERT and ClinicalBERT is also out there. So SciBERT is the most robust one out of those three for most of the problems that I've looked at. ClinicalBERT has done pretty poorly on virtually any task that I personally tried to use it for. There probably are tasks where that makes more sense, but so far, any of this pre-training on, I believe, Mimic, which is the same collection that we used here, and PubMed, I believe, hasn't turned out to be super useful. Right? So we tried to use this for de-identification of patient records, for example. So if you want to find out any name, any phone number, and all of that that's being mentioned, right? Just so that you can de-identify and then hopefully share for research purposes this data. We tried to use a lot of these pre-trained models for that, and it turns out that the general ones are a bit more useful than the supposedly clinical ones.
Got it, but there's still more specialized models that work better in the clinical field, at least in the text direction, you'd say. But in image classification, the general features just for models trained from ImageNet work just as well.
Yes, yeah. So you'll see, and I think a few years ago this raised eyebrows, but now it's very common practice to say, oh, in order to find occlusions in the brain, we'll first classify dogs and cats and frisbees and all that stuff in ImageNet. And once we're really good at that, we throw away all the sophisticated, more concrete layers and just take our edge descriptors that are now super duper 10 million images proof. And now we learn on maybe 20, 30,000 images that we have of just CT scans or whatever. Yeah.
Got it. Thank you.
Cool. All right. Last call. Anyone else? Okay. So what's next for you guys? So how many talks are you still doing until you're done with your summer?
I think we have one.
I'll keep going, Jason. My bad.
We have one left, two left.
Okay, cool. All right.
Yeah.
Well, I would say thanks for having me. This has been fun. I hope this was interesting and somewhat understandable. And let me know if I can help out in the future. Otherwise, enjoy your Sunday.
Thank you so much, Dr. Eickhoff.
Bye-bye.
Have a good Sunday.
Take care.